Yes, hi guys. Today I will talk about the last topic of this topic. Okay, the last, lecture in this lecture of mine. This continuation of this topic, expansion of functions. Okay, so today I'm talking about what is second mean value theorem, which is known as Cauchy's mean value theorem. Okay, who was Cauchy? I will just talk about the brief history of his, because history is not mine. But let me discuss about some contribution of these mathematicians, because these people have contributed a lot in the field of mathematics. Whosoever has contributed, in mathematics, I will talk about that person's history, a brief history of that person. So that is my main aim. Okay, and if I have talked about some person, a mathematician's history before, in the previous lectures, then I will not repeat that because it's the basis of time. Okay, but I have to give the brief introduction of Cauchy's. I will just talk about, and after that, what is mean value theorem? What the mean value theorem mean? What is the statement of this? Then I'll prove it. Okay, and second topic I'll talk about. There are two results which are based upon Lagrange's mean value theorem that I'll talk about. Second topic is then the fourth one. The two results which are based on Lagrange's mean value theorem I'll discuss about after Cauchy's mean value theorem. Then the fourth topic, I'll talk about what is Taylor's theorem for finite form. This is known as finite form. This is also mean value theorem in general form. Okay, this is the most appropriate mean value theorem, or as a general form. Okay, from that we can get every other kind of mean value theorem. So that is known as Taylor's finite form. Okay, Taylor's theorem for finite form. Okay, Taylor's theorem in finite form, that I'll talk about as a fourth question that I've written down here. And then finally, what is Taylor series? Okay, so Taylor series I'll talk about finally, and that will end the topic of this. Detailed expansion of functions in detail. So that will be complete topic. Okay, next I'll talk about next topic. I'll just brief that about in the end of this lecture. So let me just talk about the brief history of what is Cauchy's mean value theorem. I've written down there. Just introduce here what is Cauchy's mean value theorem. Cauchy's mean value theorem. Okay, this is Cauchy's mean value theorem I'm talking about. Okay, what is the statement? I'll just write down here. But before that, let me give the brief history of his. Okay, he was a French mathematician. Okay, born in France. Okay, and he was born at Paris in France. Paris is capital of France. Everybody knows. Okay, so he was a French mathematician basically. He was a physicist and mathematician. Physicist means a scholar of physics. Okay, mathematical physics and mathematics was his main subjects of his studies. He was a prolific writer as well. Okay, he has written 800 research materials or articles. Research articles. Okay, 800 research articles. He was a prolific writer. That he has written these 800 research articles, and after that he had written 5 complete textbooks as well. Okay, so he was a prolific writer, undoubtedly. So what was his time period? Let me note down briefly his complete name. His name was his complete name was Baron Augustin. Let me write here. His name was Baron Augustin Louis Cauchy. Baron Augustin, Louis Cauchy. This is Louis Cauchy. Okay, his was complete name. His complete name. Date, time period was he was born on 21st August. Because that maybe his name is Augustine. Okay, that is because of Augustine. So he was born in August, 21st August. 21st August was his birthday. 21st August 1789, and died on 23rd March, and died on 23rd May. And died on up to 23rd May. He died on 23rd May 1857. Okay, so this was his time period, 21st August is 1789 to 23rd May 1857. Okay, during this period he was worked, and his basic subject of study was mathematics. He was a professor of mathematics. Okay, mathematics and physicist. He was a physicist or mathematical physics. Was a good scholar of mathematical physics. And second thing, he was so much scholar. I mean, his in his name there are 16 theorems or articles or whatever. They are famous in mathematics. About 16 theorems or topics which are named after him, after his name. Okay, so his name is famous for a number of theorems. Okay, so Cauchy's name is very famous in mathematics. So he was mathematician from France, basically a French mathematician. This is a brief history of his. Okay, 800 articles he wrote down. Let me write about his. Was a prolific writer. Was a prolific writer. Was a prolific writer and wrote 800 research articles. Okay, and 5 complete textbooks. 5 complete textbooks. So this is basic contribution, and 16 theorems or articles, or basic theorems or axioms in his name in mathematics. Okay, in the field of the subject. So this is a brief history of it. Now come to the main topic. What is his theorem then? The basic theorem given by, this is known as mean value theorem by Cauchy, or Cauchy's mean value theorem. What is his theorem? It is just right that there are two functions. If fx and let me take phi x, these two functions, the two functions are continuous in closed interval, that means this is closed interval AB, or A is less or equal to X is less or equal to B, and both are differentiable or have differential coefficients, differentiable at every point in the open interval, open interval AB, that is A is less than X less than B. Okay, where f phi x and fx, and here phi x is not equal to, here both phi x and fx cannot vanish simultaneously. Phi x or fx cannot vanish simultaneously. This is fx and phi x do not vanish simultaneously, that are written down here, where phi dash x and f dash x do not vanish simultaneously. This is the most important point. Do not vanish simultaneously. Okay, this is one of the points here. Then, okay, then is FB minus FA. Then FB minus FA. FB minus FA divided by phi B minus phi A, that I have given there, okay, equal to, if I have taken, suppose f dash C, it may be C or zeta I have taken there, so let me write here zeta, no problem. It is the zeta point, and this is phi dash zeta. A point zeta, where zeta lies between A less than zeta less than B. In the open interval, zeta lies. Okay, so zeta lies in AB. So this is the theorem given by Cauchy. Okay, so Cauchy's, this is known as mean value theorem by Cauchy. Okay. And how we have to prove this? Here it is given to us that phi b is not equal to phi a. Here phi b is not equal to phi a. Otherwise it will become Rose theorem, because then fb equal to fa, because this is 0, 0 equal to 0, fb equal to fa then. So that will become Rose theorem. So this is not equal to this. Okay. Now let us prove it. Now proof of this, how to prove it? Okay, let us consider. Okay, let us construct a function. Let's construct a function fx equal to, fx equal to, here it is small fx plus a into phi x. This I take it here. What does it mean? Here a is a constant based on that f equal to 0. Here is, we have constructed this equation. Let me take this in one function, also equation 1. Here a is a constant based on the assumption, what is the assumption here? That fa equal to 0. On this assumption, this equation is based. Fa equal to 0. Okay. If fa equal to 0, if I substitute here fa equal to 0, okay, and fa equal to fb, this is also the equation. Fa equal to fa equal to, not x equal to 0, but fa equal to fb. Fa equal to fb. This is the assumption here. Okay, so let me use this assumption, or fa equal to 0 as well. Assumption was fa equal to 0 as well. So fa equal to 0, if I substitute here, then this will give us f0 a into phi dash 0. That will become the Rose theorem. So that is fa equal to 0 or fa equal to fb. Okay, if I apply this fa equal to fb, okay, this is given to us. So if I apply here fa equal to fb, we will get a equal to here fa from the first equation. This is based on assumption fa equal to fb. So fa is equal to, in this case, fa plus a into phi a, and fb is equal to, by substitute, is fa equal to fb. This is assumption, and this assumption fa is not equal to 0. Only this assumption that fa equal to fb. This we have taken here. If a is based on this assumption that fa equal to fb. So in this case, if I substitute fa, so fb is equal to, then this is fb plus a into phi b. Okay, so from this third, and let me take fourth. From third and fourth, what we get? Let me write it here. So from third and fourth, we get fb plus a into phi b is equal to fa plus a into phi a. That means if I solve it for a, is a plus sign. So a, if I take, that will give us, let me take f phi b minus phi a. This is a into phi b minus phi a. This I have taken here. This is equal to minus sign. Let me take fb minus phi a. Fb minus fa. This fa. This phi a and phi b I have taken together here. This is minus sign. I have taken this that side and take minus sign common. So fb will be positive and this will be negative. So that is what I have done here. This is minus sign I have taken here common. Okay, opposite sign A is positive, so minus 1 plus. The same thing is there. So A is equal to, in this case, so what we get here, so A is equal to, with minus sign, this is FB minus FA oblique phi B minus phi A. Okay, so this is, we get, or minus A is equal to, let me write here, minus A is equal to, this FB minus FA divided by phi B minus phi A. This is phi A minus phi A. Okay, FB minus FA upon phi B minus phi A. So that is equal to minus A. Let me take this as the fifth equation. Okay, this was the, I think, fourth equation, whatever I've taken there. So now let me take the answer. Now it proves, now it satisfies the Rolle's theorem. All the conditions of Rolle's theorem are satisfied. So all the conditions of Rolle's theorem are satisfied. For example, are satisfied. That means first one is FA is equal to FB, that we have taken here. Okay. Second is f dash x exists. F dash x exists in the open interval AB, in the open interval. Okay, let me rub this. In the open interval AB. Okay, and third point is that there is a point C, or f dash x exists at A dash C, f dash C equal to 0. Okay, so f dash C equal to 0 we can have here. Now from the given equation, this one, f dash fx we were having, this was fx, okay, plus A into phi x. If I find out f dash x, from this will give us f dash x, okay, plus A into phi dash x. If f dash c, if I substitute here, okay, or zeta, if I've taken zeta here, I've taken zeta here, let me write here f dash zeta. Because f dash x exists in the open interval, therefore f dash zeta equal to 0. So if I apply this here, f dash zeta, if I substitute this in this equation, f dash zeta, let me write here, is equal to f dash zeta, is capital F dash, plus A into phi dash zeta. Okay, or f dash zeta equal to 0, if I substitute this equal to 0, this implies that from this A into phi dash zeta, A into phi dash zeta equal to minus sign this one f dash zeta. Okay, or A is equal to, therefore A is equal to minus sign f dash zeta oblique phi dash zeta. Okay, so value of A or minus A is equal to this. If I equate this from this is suppose fifth equation. So from fifth and fourth we get, from fifth we have minus A is equal to, this is f dash zeta upon phi dash zeta. This was fifth equation, and fourth was minus A is equal to this value fb minus fa upon phi b minus phi a. So equating this is fourth equation. So from fourth and fifth we get the result. So equating this value of minus a from fourth and fifth we get fb is this is FB minus phi B, minus FA, FB minus FA upon phi B minus phi A equal to F dash zeta oblique phi dash zeta. Okay, so this establishes Cauchy's theorem. Hence, Cauchy's theorem is proved. So we have to assume that function fx equal to small fx plus a into phi x. Okay, this after that we have to make Rolle's theorem, Rolle's condition satisfied, and then this result can be obtained. So this is Cauchy's theorem we have proved. Okay, these results are given there. The statement is given in the first question here. The whole thing is provided that phi a is not equal to phi b and f dash s and phi dash s do not vanish simultaneously in AB. So that I have written down in the first question. Okay. Now let me take the second and third questions, which are very important. Second and third question here. These two results are based on Lagrange mean value theorem. Okay. So what was the Lagrange mean value theorem? Let me take the second question here. Now, second question is, it says from Lagrange mean value theorem. Okay, can be written. We were having Lagrange mean value theorem. Let me first define that, or let me write the result of Lagrange mean value theorem. This we have talked about. We have discussed in the previous lecture. Okay, the 39th lecture. Now, Lagrange mean value theorem. Mean value theorem. This I have discussed in the previous lecture. So, what is the result of this? The result of this was FB, okay, minus FA divided by B minus A is equal to F dash C. This was the basic result, okay, of Lagrange mean value theorem. Now, this result can be written as I have written down there. FB minus FA equal to B minus A into F dash C can also be written, okay, in this form. Now this form is known as, this is incremental formula, known as incremental formula. Frequently it is known as incremental formula because FB minus FA, what is the difference of this? What is the increment of this? This is equal to B minus A into F dash C. Okay, so this is known as incremental formula. This form is usually known as incremental formula. Incremental formula. Okay, generally it is known as incremental formula. So incremental formula, it is known as formula for finite increments. Okay, or incremental formula. Okay, this region, the result is known as incremental formula. Now let me discuss about what is the incremental formula in this case. So let me take, let C is a point, as we know, the C is a point lies in AB open interval. Okay, because F dash C we always find out what is F dash C here. F dash C is 0. It's F dash C because C point is lying in AB open interval. This is given to us, and okay, this function fx is continuous in the closed interval. Okay, so that is the basic conditions of Lagrange mean value theorem. That function fx given is a continuous function in the closed interval and is open interval AB. There is a point C at which F dash C equal to 0. Okay, and that we will take. So here C is a point, or C is interior point of B. At C, not left, but here C is a point lies in AB, or is the interior point. Is the interior point of AB. Okay, so C lies in between AB. Is the interior point of this open interval AB. Now, okay, so final result is you can know this. Okay, Now let me express this in another form. So what is the final result of this then? Sorry. So final result of this is known as okay, so this interval of AB. Now let me write here C minus A upon B minus A. What is the difference of this? Now let me talk about this. C minus A, I've taken this C point in the interval of AB. Let me write here. Here it is A, C and B. This is the open interval. This is the open interval. C lies in between AB. We cannot say this is the middle point or something. It may lies towards A, it may lies towards B. Okay, in the left hand side or right hand side, that doesn't matter. So the difference of C and A, this difference, is smaller than difference of B minus A. For B minus A is the total length of this interval. B minus A is the total length of this interval. But C minus A is smaller than B minus A. So this is lesser than 1. This value will be less than 1, but positive. Okay, so let me take this is equal to theta. Here theta is 0 is less than theta is less than 1, because this value is smaller than 1. We have taken C minus A is smaller than B minus A. B minus A is bigger value. If denominator is bigger and numerator is smaller, then this value is less than 1. So this value equal to theta I have assumed. So theta lies between 0 and 1, less than 1 but greater than 0. Okay, so we can write it as C minus A is equal to theta into B minus A, or C is equal to A plus theta into B minus A. So in place of C, we can write this A plus theta into B minus A. So this can also be written as, or further it can be written as C equal to, in place of C we can write this as this. Okay, and if I take B minus A as H, and B minus A equal to H, if we take this interval B minus A as H, then what is the value of this C? This implies then C equal to A plus theta into H. C equal to A plus theta into H, or here B equal to A plus H. Okay, so value of B is A plus H, C equal to A plus theta H, or A plus theta into B minus A. So this we have taken here. So B equal to A plus H. This theorem can also be written in the terms of this. So let me note down this result of Lagrange mean value theorem, which was in incremental form. It can be written B equal to A plus H. This is F into A plus H minus FA equal to, this is H we have taken, and F dash C is A plus theta into H. A plus theta into H, C is. Okay, so this can also be written in this form. This is second form of this is first form. Second form, the same similar function. Okay, and if I've taken this C, or as FB minus FA, if I just write only this is B minus A, that was B minus A into F dash C. In place of C, I could write it as A plus theta into B minus A. This is also one of the forms. Okay, F dash A plus theta into B minus A. This is also one of the forms. So this is how we can note down this form, this theorem. So these are the different results based on. So here we have taken C is equal to A plus theta into B minus A. Here B minus A is equal to H we have taken. Okay, so this is also the formula H into F dash A plus theta into H. Okay, so these are the results based on this. This is another form of Lagrange mean value theorem. Now next is third one. Let me talk about what the third says. Third says from Lagrange mean value theorem, this is also the result. Third result is also based on Lagrange mean value theorem. It says function, if fx, the function, has a derivative that vanishes for all values of x in the interval AB. That means function is a constant function. Okay, and vanish is that in the closed interval AB at every point of this, then the function is a constant function. Moreover, if two functions have derivatives that are equal for all values of x in AB, okay, then the function differs by a constant. Okay, the function differs by a constant that we have to prove here. That what is the function here? So here it says that fx is if fx the function fx vanishes, okay, at every point of open interval or close of open interval close, this here taking close interval of a less or equal to s less or equal to b, then fx is a constant function. That means fx equal to, let me take this fa, this is a constant function. So fx equal to fa, a constant function. But if I differentiate it, it will be 0. So a constant function. So derivative of this f dash x will give us 0. Okay, now let me prove the second result I have to prove here. So the second result here, or is a constant, if I take constant as fa or whatever, that is given to us, that fx equal to fa is a constant at every point, because we find out derivative at any point in this interval fa or fb. If I have taken this fa and this whole function is 0, okay, so f dash x is 0 in any way. In this interval, if I take it as c or any point in between ab, then this function is 0. Now let me take that fx, to prove the second point. It says that if there are two functions, moreover if two functions have derivatives that are equal for all values of x in AB. Okay, that means let me take fx equal to fx1, there are 2 points fx1, x1 and x2. Okay, let 2 points x1 and x2 lies in AB. Okay, so fx1 and fx2 have the equal function. It says, if I find out the derivatives of these two functions, that will give us equal derivative. They say, so if two functions have the equal derivatives or have derivatives that are equal